Oh, good morning, everyone. Can you hear me well? Yeah. So maybe before I describe the outline of these lectures, maybe let me say a few words about the main goals. So, or the main applications of what I will talk about. So, one of the main application is of the sort of more abstract things I will talk about. One main one is the S matrix bootstrap, which plural, which as we've seen in previous lectures, there are many instances of it. There are some non-perturbative bounds that one can get on effective theories, as was discussed by Henriette. There are non-perturbative bounds on strongly interacting theories that Lucia will talk about. In some sense, a lot of perturbative bootstrap is ingrained in the modern amplitudes program. We try to guess scattering amplitudes based on general properties and what kind of function they can be. You get recursion relation and so on. So this will touch on these things. So essentially, I want to try to explain, okay, why we believe in dispersion relations and these analytic properties and all these properties. Why we believe that. That's the first lecture. So talk about something else which is important in amplitude is that the fact that when Minkowski signature, uh, the amplitudes we compute have complicated analytic properties, analytic of amplitudes. And I want to describe a few things that we actually know about, when we explore an amplitude that are a function of various momenta, energies can be incoming, outgoing, you have various channels. There are some ways that we understand to connect them, and there's probably a lot more to explore, but we'll try to describe some things that we already actually know about it's good to have things that we know for certain about these complicated functions. The other thrust of this lecture will be that when you think carefully about these analytic properties, you're led to think about other observables than the cross-sections that we grew up learning to compute. And some of these observables include inclusive quantities, like impulse, waveforms, and so on. They're particularly interesting in gravitational context, but they also make sense in the particle physics context. So basically, lecture 2 would be about introducing this observable, and lecture 3 would be about some formalism that is very scary to most people, but it's not going to be scary after you go through a few exercises and do it. And this formalism really helps you understand dissipation and various phenomena that occur when you scatter complicated objects. Okay. And yeah. So that's the goal of these lectures. There should be plenty of time, so feel free to interrupt anytime. Yeah. Question on this plan? Yeah. So today I want to describe okay, what is causality about? What do we mean and why we care? Uh, so we care specifically about relativistic causality, which is the notion that signals cannot travel faster than light. Let me write it down. Then the speed of light to some fixed speed. And, and that's a very striking property that is very at it's really at the heart of particle physics. When you think about it, maybe a general comment also on this, some of these axiomatic issues that we talk about, there's a widespread belief that we're basically recycling results from the 50s and 70s, so why in 60s, so why is this interesting? I'd like to dispel this impression because a lot of the ideas are actually much older than that. I strongly disagree. But also, a lot of the actual technical developments, modern developments, there's a lot of new ideas, as we've already heard in the past 3 lectures. Past 2 days, there are actually a lot of new ideas there. So there's nothing we fully understand there. So, okay, so So coming back to the very ancient days, here's the example of what this tells us. So imagine you have a decelerating charge, electric charge, that stops at the origin. So you have a decelerating, you have a charge that decelerates. And you ask, what's the force that it exerts on some other electric charge somewhere else? And after the charge has stopped, well, you know that there's some kind of electric field that's radially pointing outward from it. And that is kind of the new field after it stopped. And however, the fact that the charge has stopped, this information is not communicated instantly to the whole universe. If you're sitting at a remote point, like this information only goes the speed of light. So far away, there's some old point where it's somehow pointing towards the old place. So this old field. And they're separated by some shell of radiation. So this drawing is taken from a textbook by 1903 by J.J. Thomson, who was explaining why it is that the accelerating charge this radiates. And the sort of nice thing about this argument is you can turn it around. It tells you that if you don't want action at a distance, any force has to be associated with some wave. Because you move something, you change the force, can't change instantly. And also, because the force is energy, so the wave has to carry energy and momentum. So this principle explains why we care about fields in nature and why these fields need to satisfy equations that have wave solutions. All forces in nature need to be associated with fields that have wave solutions. And of course, in the quantum theory, once you know that these waves carry energy, you also know that this energy has to come in discrete units, discrete packets of energy. And this is why we have particles. Right. So in particle physics, we're obsessed about explaining all the interactions in the world by exchanging particles. But the reason this has to work is this principle. You can't have action into distance. Okay. And there are many more sophisticated arguments. Some of them we'll see toward these lectures. You can do more refined arguments that tell you that whenever you have a particle, you need the antiparticle with the opposite quantum numbers. Tells you why the scattering amplitudes of antiparticles are related to those of particles, so that's crossing. Basically, why we do QFT. But the main point of the lecture also would be that it's not just telling us why we do things, it also helps us concretely calculate things. Okay? So it's a tool to calculate, to do concrete calculation. Okay? And in order to convey this argument that causality is very important to what we do, I'm going to propose to you a little exercise, a little homework that you can actually do during this lecture. Which is to write down the quantum theory of gravity, solve the quantum gravity problem if you don't care about relativity. So problem is to make a unified theory of the standard model, or whatever is your favorite quantum field theory, and Newtonian's gravity. Okay. So write a quantum theory of Newton's gravity plus your favorite QFT. Okay. It's really easy. You can all do this during this lecture. Think about it. Okay? Surprisingly easy. Okay. Do I have the right to use some of these boards? No, I will not do that far. Do you have is there a free one? Yeah, yeah.
Sorry, do you
Yeah.
want a non-relativistic QFT?
No, it could be the standard model, but the whole combination of them doesn't have to be relativistic. Okay? You know, try to do some, and maybe if you just do it like this, maybe it won't quite describe nature, but try to do something that describes known experiments about nature. That's the general idea. So I want to make a general comment also about the fact that causality is something that we observe on vastly different scales. So, so perhaps most obviously, it's seen at very large distances, like astronomical distances. So for example, supernova explodes, you see neutrinos, and you see the light coming a little bit after. They come a little bit after because it is delay in the way they ascend, but they travel like 100 million, 100,000 light years to you, and they still arrive basically in sync. Also, gravitational waves from this is famous event that was the birth of multi-messenger astronomy. It was a gravity wave, and 1.5 seconds after, there were gamma rays coming from hundreds of million light years away from here. So things really, like signals really don't exceed this velocity of light. It's also seen at very high precision, by which I mean that a lot of these predictions, like the existence of antiparticles with the same properties, can be tested with exquisite accuracy. So for example, the energy level of antihydrogen over the energy level of hydrogen are basically like 1 to the 10 minus 10 level. Okay, you can do atomic physics experiments, test that. You can check the charge, you can check the mass of the electron and positron, these sort of things, and they really all come out the same to exquisite accuracy. They also work at very short distances. And this is something which is perhaps a little bit more striking. But for example, in colliders, we make quarks and anti-quarks that we describe using quantum field theory, with interaction with our described using quantum field theory. And if their properties were not the same, we will just see it. Okay? the whole, all the LHC cross-section plots will be off. So basically, we're probing, that's effectively probing causality at this Compton wavelength that are being probed, which is like, 1 over 10 to the 1 over TV or something. It's something like 10 to the oh, but yeah, something like 10 to the minus 19 meter or 10 minus 27 second. So when you put these numbers in perspective, this is not like we usually think about relativistic causality as something like to avoid paradoxes, like you go back in time and do something nefarious to your grandparents. Why this obsession about grandparents? But like nature cares much more deeply about this. It cares about this principle even to tiny, tiny time scales. Okay? So that's what I want to say. Maybe a little historical comment. This is experiment. Anyone here heard about the OPERA neutrino experiment? It marked a generation. It's great, you're true. It's great that you never heard about it. It's fine. So there was an experiment around 2011, I think, about it's an experiment that measures neutrino, very high energy neutrinos, like tens of GeV sent from CERN to a mine a few hundred kilometers away. And they timed the travel time very carefully. And they found that the neutrinos systematically arrive 60 nanoseconds faster than speed of light. And that creates a lot of puzzlement and a flurry of activity. In fact, it was very puzzling. It was a very puzzling time because it was also quickly realized that this measurement was also not compatible with basic physics that we know. So, for example, when the particle when something moves faster than the speed of light in the surrounding medium, you get Cherenkov radiation. And so if something moves faster, if a charged particle were to move faster than light, we'll just Cherenkov radiate to death and it would just stop. And now neutrinos are not charged. Well, they have weak charge. So you could have a process where a neutrino through a virtual W boson, Cherenkov radiate electron-positron pair. And it was calculated that, and if the neutrinos have a huge energy, the electrons are basically massless, and then this process exists. And it was calculated that this process will basically have depleted the beam by the time it got to the mine, if the neutrinos were indeed moving that fast. So it was a very puzzling measurement. And the experimenters realized it was puzzling. So they went out and asked people, please help us replicate this and find what the error. And it turned out that it was a loose cable. Life is really cruel. Sometimes there was a loose cable that was connecting the GPS receiver that they used to synchronize clocks with the device. And the loose cable caused a signal to bounce, and they were using the bounce signal to set their time. It's very painful, but it's science. Sometimes it's painful, and eventually you get the truth. So in the end, it was just a loose cable. And the experiment was replicated by other groups, and they all agreed with the speed of light. Yeah.
Could you just re-explain what the setup was? I'm not sure I understood.
Yeah. Yeah. So there was a so the way you make a neutrino beam is that there was a SPS collider at CERN, and you have something going on a ring. You accelerate electron, I think maybe muons, and then you hit them on a wall. And then the muons hit the things in the wall. The muons, I'm not sure what they're scattering. Take what I say with a grain of salt, but they hit something on the wall. And then some weak interactions occur in this wall. And the neutrinos that are produced, they just keep going straight because everything's transparent to neutrinos. And here, because they know exactly the timing of this beam, the particles come in bunches. They know exactly when these neutrinos left CERN. And then there's some mine somewhere else where you have a tank of water that serves as a neutrino detector. And you time exactly when this beam arrives. And the timing was important to the general goal of this experiment was to measure oscillations of the neutrinos to, I think, detect tau neutrinos, I think. And it's very useful to have good timing because you can do coincidence correlation with your measurements. So they had good timing, but they just noticed that it always came 60 nanoseconds faster than they thought. When's the puzzle? Thanks for the question. So, yeah. Okay. Okay. Now we'll get into the gist of dispersion relations, which will actually motivate from a model. This is first, the next few minutes are basically going to be a signal processing class. So we're going to try to understand what causality means for a wave. So in a signal processing class, you imagine you have some pulse. Let's call it some in pulse that you throw into a black box. It's copyrighted. You can't look inside. And out comes some out signal, which normally doesn't quite look the same. And here it's going to be useful to think either of these axes as time or x. So if you imagine your wave is moving to the right, the beginning, you can either record the wave at a fixed place, function of time, or just take a snapshot. These two perspectives are useful. And I'm going to make a few simple assumptions about the box that are going to be relevant for particle physics, actually. One is that the box is linear. I'm going to spell out what exactly that means in a second. We assume that it's translation invariant, time translation invariant. We're going to assume that it's causal and 4 unitary. Okay, so let me explain this thing in turn. So a linear box is pretty much the linear thing that we study in classes. And it's just the idea that this out signal is related linearly to the in signal. So something like this. So psi out of t will be some integral over t prime of some kernel t minus t prime of the in signal at t prime. Okay, so the sum relation, the sum integral transform that takes you from the in to the out signal. That its translation invariant means that this k, sorry, only depends on the time difference. And that also means that you can go to Fourier space, and in Fourier space, momentum frequency is conserved, so it's just multiplication. Out of omega is some multiple of psi in of omega. Right? So for each frequency, you get to be multiplied by some transfer function S, which I call S because it's going to be loosely related to the S matrix. I think that takes you from the past to the future. Now the box is causal. What does it mean? Well, the idea is that if you had a signal that was 0 up to some time, that only start at some time, if your input only starts at some time, then your output should have the same property. That's the idea of causality. So the statement is that if psi in of t equals 0 for t less than t0, and that implies the same for psi out. Okay. Well, up presumably to some offset from the travel time. Okay, I'm gonna have to subtract the naive speed, the wave moving freely at the speed of light. Okay, so with suitably normalized time, you don't advance. And unitary, that basically means that there's some square norm of the signal that's preserved, or at least cannot increase. So I mean this following. So if you integrate psi in square, sorry, if you integrate psi out square, that is less than the integral of psi in square. Okay? And I'm going to allow less than because, maybe the signal gets stuck in the box and doesn't come out, right? Maybe it's inelastic, okay? But it shouldn't be amplified anyway, okay? So, yeah, could be absorption, but no amplification, okay? And by Caron-Huot formula, we can also write this in Fourier space. So the square integral of the signal in Fourier space also does not go, right? Because it's the same integral of the square of the wave function is the same in any representation. Yeah.
So I don't know what because this is the classical picture, but
Yeah.
in unitarity in quantum physics, we have like three notions of unitarity, and here you seem to be using the preservation of norm of unitarity only.
Yeah,
But
it's a good question. So let's interpret this. So classically, so in order to make sense of this, so first of all, here it really comes handy to think about x instead of time. So because normally we don't integrate over time, it really makes more sense to integrate over x. So I should really put x here. So in classical physics, the integral of some amplitude square over x give you the energy. Okay, so this is like, so classically, this is energy conservation. Classical, that's energy conservation. On the other hand, if you think of psi as a wave function of a particle, also a function of x, then this is a statement that probability is conserved. So in quantum, it would be P conservation. So depending on the setup, this can have different interpretation, but it's a natural assumption in these situations. Okay. And probability conservation, like the probability that your particle come out can be less than 1 if there's a non-zero probability that it stays in the box. But it can't be bigger than 1. Okay.
thank you.
Yeah. So the implication of 1 and 2, I just wrote down in the definition. The implication of 3 and 4 are a bit more subtle. And I'm going to quote a theorem and then explain it. Okay. So if you have causality and unitarity, it turns out to imply that this transfer function, S of omega, is analytic in the upper half plane and also bounded in the upper half plane. Where bounded is actually strictly less than 1 in this.
Simon, can you write a bit bigger?
Yes.
Thanks.
Yeah, it's an important theorem. Maybe I will actually rewrite it. And so true for the whole upper half plane, it's less than 1. Okay. The fact that it's less than 1 on the real axis is kind of trivial from this relation, because if you were to imagine an initial wave function that's peak around some frequency, and if you were to multiply it by some large number, you will violate this unitarity condition. So this is clear on the real axis, but the claim is that it actually holds everywhere in the upper half plane. Okay. So this theorem is proven in this nice proof in the paper by Kamano, Edelstein, Malesena, and Zhiboidov, appendix D. I will not go through the proof, but I will describe why these assumptions are important for this result to hold. Okay. Yeah.
When you interpret this unitarity as a energy conservation, I'm confused by a reason that what if there's some superradiance happening and
then this will not apply.
It would not apply. It's you're saying superradiance just violate the unitarity. Is that the statement?
This particular statement, superradiance will violate the statement about the norm square of the amplitude. Yeah.
I see. Okay.
So or more generally, but So for application for this matrix, I will where really unitarity is a sharp statement, I would keep this statement. Okay. So let me first explain what NLST is good for. Okay. So I think the best way to understand it is actually not from the Fourier transform, but from its inverse. So look at the inverse transform. So we're going to look at the inverse transform. Suppose you have a function f of t, which is the integral of some Fourier integral of f of omega times x of minus I omega t. And we claim that when this function is analytic in the upper half plane, this describes a function t which only only supported at positive time. Okay, so a concrete example will be f of omega equal I over omega plus I. Concrete example. Okay. I claim that if you compute this integral, you get 0 whenever the time is negative. It's a claim. If you stare at this, that's not really obvious, right? Because the integral, like, literally is telling you to add this oscillatory thing. You add up all these oscillations weighted by this thing. And the claim is you add up all these oscillations from minus infinity to infinity. They add up to 0. Like, I don't know about you, but I cannot just stare at the oscillator integral and see that it adds up to 0. Like, I can't do that. But there's a trick. There's a method to do this. Here's the method to estimate Fourier integral, oscillator integral. It's something you can apply to any oscillatory integral. And the trick is to use the complex plane. So the trick is to note, if you look specifically at this factor oscillates a lot on the real axis. But notice that if t is less than 0, so this looks like x of plus I omega times something positive, this factor, if I were to add a positive imaginary part to omega, will actually decrease. Right? So decrease with the imaginary part of omega up. This means that if you think about the integral in the complex plane, if we're starting on this contour, I wrote an integral that had the pole here at minus I. And what I'm telling you is that the integrand decreases if you push the contour up. And that's how you can estimate this integral, because the integral is simply, what you estimate of the integral is it's as small as you can make it by pushing the contour. So step 2 of this method is that integral will be at least as small as you can make it by shifting the contour. Be as small as you can, let me draw it, you can make it by deforming contour. This. Oh. In this case, in this example, nothing obstructs you from pushing into infinity, and that's why it's 0 on the left. Or less than 0. However, when you flip the sign of t, now instead of the other behavior, the integral decreases in the lower half plane. Now you try to push it, but you get stuck at this pole. So the integral for positive time is given by the residue at minus I, which gives basically x both minus omega t worse than 0. So in general, you have to stop in either of two situations. You stop either because you hit a singularity, a place where the integral is not analytic. Well, stop at singularity of integrand. of f of omega. Or it could happen that the integral, as you keep pushing up and up, eventually stops decreasing and starts increasing again. And then, well, you should not push further, it should stop there. And that generally happens when you have a saddle point, or the place where the derivative of the function is, or its saddle point. Okay. Here's another example. So if you have a function that is a Gaussian in frequency space, the Gaussian is analytic. So you might think, well, its Fourier transform is going to define a function which vanish at positive times. But of course, you know that the Fourier transform of Gaussian is a Gaussian, so it's not true. What's going on? What's going on is that it's analytic, but it grows exponentially in the imaginary direction. It decays along the real direction, but it grows like x plus imaginary part of omega square in the complex plane. So eventually, the total integrand, which is x minus omega square over 2, plus I omega times the root of t, the smallest you can make it is somewhere in between when you balance this decaying term with this growing term. Omega over 2 is minimized at exponential at some time, sorry, at some frequency over the imaginary part of frequency over the t, where its size is about x of minus t squared over 2, which is the size of the Fourier transform of the Gaussian. Okay? So what we learn from these two examples is a general statement, is that if you only have causality, causality is equivalent in Fourier space to having analytic in upper half plane plus not growing faster than any exponential in the imaginary direction. It's called sub-exponential growth. In imaginary part of omega. Okay? So causality is really not just analyticity. It's also a statement that the function is bounded. Okay? If it grows exponentially, analyticity doesn't buy you anything. Because the only reason you want to deform the contour and use analyticity is that the function is decreasing. It doesn't decrease, you don't play this game. Okay. What I like about this method of estimating Fourier integrals, so you can use this method to estimate any oscillatory integral, trying to make it small before you integrate. What I like about this method is that it makes it clear that it's very stable. So if you have a little bit of non-causality, you're going to have a little bit of non-analyticity. Okay? So for example, there's a bit of a parenthesis, but yeah, if you had a little singularity here, maybe let me draw it to a different color. If you have a singularity here, you will have a non-analytic, you have a non-acausal behavior that goes like x to the minus absolute value of t times, let's call this point omega 0, times imaginary part of omega 0. So if analysis fails because you have something, singularity far from the complex plane, well, causality will fail, but only if the time is very small. Okay? So that's what this argument makes clear. Okay? So it's not, so analysis is not like this all of nothing thing. You have it or you don't have it. If you break it a little bit, then okay, you have a little bit of a causality. Okay? We're going to study theories that have no causality at all. Yeah.
Is this in some way manifestation of the uncertainty principle?
Yeah, there is a relation. Yeah, there is a relation in the sense that that the position of the singularity is related to the time at which you will, and related inversely to the time you will see it. Yeah.
Thanks.
Okay. Okay. And so that explains this analysis and boundedness, why they're both important. And maybe let me grab that. This one. Now we're going to make another example. Which is just slightly more realistic or relevant. We're going to imagine that our black box, damn, this does not erase very well. We're going to assume that our black box is some medium with some dispersion relation. Okay. Another example, last example of today. Imagine that the black box is, so the box is a medium with length L and dispersion relation K of omega. And refraction index N, which is K over omega, which in general will be a function of omega. Okay. In this setup, you throw in a wave that goes like x bar by kx minus I omega t into the box. And then it comes out, when it travels to the box, k is different. After it comes out, k is back to be the same. But the fact that k was different during the box gives you this extra phase. That is x of I omega n of omega minus 1 times the length of the box. So this is the transfer function that corresponds to this box. It's related to the index of refraction and the length of the box. Okay? I'm just making a simple natural optics problem here. And the signal we send, we assume the signal is some kind of Gaussian wave packet that's narrowly peaked against around some frequency omega 0. Okay? So something like this. Draw some envelope. And the trick to drawing these things is to draw the other envelope on the downside. And then you can draw some little wave that goes between them. Okay? And the frequency of this wave is omega 0. Okay? Well, these are some shapes, some wave packets. Okay? So we throw this wave into this medium, and the question is what happens. Okay? Okay. A lot of, before we say anything non-trivial, we have to review the very basic concepts. So, well, if the wave packet is narrowly peaking on some frequency, what you will do is you will Taylor expand, right? You take n of omega, goes to n of omega 0, plus n prime, omega 0, times omega minus omega 0. You could do a series expansion like this, right? And this term here will basically just give you an overall phase to the thing that's going to shift this. That gives you basically the phase velocity, right? So the oscillations advance by essentially delta t will be equal to L n omega 0 minus 1. That's it. And which is the same as saying that they move at phase velocity n omega 0, which is yeah, omega over k. So n inverse is omega over k. Okay? Like the inverse of the index of refraction is this. Okay? And when you actually compute the Fourier transform, the thing you actually need to use is that derivative term, and that would give you the Fourier transform, including this eta prime, will tell you how the overall feature change, so the envelope advanced by the group velocity. This is a familiar concept, right? So the envelope follows group velocity, and we call it V group, which is in fact is d omega over dk, which is related to n prime. Okay, so this is familiar. Now the question for you, question would answer. Suppose you have a medium that has a faster than light group velocity. Well, first, is that possible? And B, what will the output signal look like if V group greater than 1? What does psi out look like? It's a puzzle, right? Can you have that? Do you take both? So notice that, so if you have a medium with a faster than light group velocity, notice that the time advance you get out of going to this medium is increased by the length of the medium. So if you can have some time advance, you can make a medium longer, and you could have a 5 sigma advance. Okay? So this is a Gaussian. You can advance by 5 sigma without any problem, which is a medium you want. I claim these things do exist. Materials with this property do exist. So if the signal advance by 5 sigma, like 5 times here, this sketch what it will look like. Can you use that to transfer information faster than light? It's puzzling, right? It's quite puzzling. So this is where analytic comes to the rescue. So what happens in the causal medium is that this dispersion relation, this n of omega, is not arbitrary. If the medium is causal, under the assumption that I wrote, this n of omega needs to satisfy a dispersion relation. This is a weird sentence. The dispersion relation satisfies the dispersion relation. What I mean is this following, is that this Kramers-Kronig relation, n of omega, is analytic in the upper half plane. As an analytic function, you can write it as a contour integral of the following type, d omega prime over omega prime minus omega psi epsilon of imaginary part of n of omega. Okay? So it's analytic and satisfies this dispersion relation of Kramers-Kronig, which is the ancestor of the fixed T dispersion relation that Mariette used in the S-plane, Manastan S-plane. The ancestor of it is just in frequency space. Yeah? A function of frequency, and it claims you can construct this function from its imaginary part. So what does this formula mean? So why do we have the imaginary part to the first place, to this dispersion relation? So physically, the imaginary part arises when you have absorption. Okay? So for example, if you throw light into air, very close to frequencies of atomic resonances, the light will get absorbed very efficiently, and that gives you a complex index of refraction. So the imaginary part measures the absorption. So if you plot this function, and as a function of omega, function of n, then close to some absorption peak, you will have imaginary part of omega from absorption. Now, if you plug this into this formula and compute the integral, you get something like, I can write an example of a resonance, it's a simple Brett-Ringer form. You could imagine having n equal to 1 plus some coupling over omega. So yeah, omega 0 minus omega minus I gamma. Imagine having something like this. This is n of omega. And we'll give you this imaginary part will have this bump. And the real part, as this property, comes out the thing that comes out of the integral is that the index of refraction is positive below the peak. And it kind of changes sign and it goes like this. So this means that you slow down. Index of refraction is greater than 1. And here, the phase velocity is sped up. Here you have v phase greater than 1. But the thing we really care about is not the phase velocity, it's the group velocity. And, well, from this n, you can compute derivative and plot the group velocity. And what it looks like is this. It is slower than light, usually, but near the resonance, it's faster than light. So this is what V group looks like. And it's a very general feature of this. You can show about this Kramers-Kronig relation that the only way you can have a group velocity faster than light is that you have absorption. These two things always go together. So V group greater than 1 is only possible where imaginary part is not equal to 0. And how this explains, we can use this to explain what you will see when this pulse goes through, when this Gaussian goes through this medium. Can you see it? Maybe the keyword is absorption. So the psi out signal will look as follows. If I zoom on the out signal, so the in signal at this envelope, and the out signal can be advanced, but it's going to be also absorbed, so this is a tiny amplitude. So the out signal will be a little bump under the original Gaussian. So the Gaussian did get advanced by 5 sigma, but it's also small. So you can't actually use that to send a signal. Okay. So advanced, and maybe it wouldn't be distorted so much, it could be smaller, but it will be advanced, but absorbed. Okay. And it's a theorem by this contour deformation argument we just made, that because this dispersion relation function, this dispersion relation is analytic on the upper half plane, it's a theorem that the signal you see here only comes, I mean, it may look like a Gaussian as advanced, because it looks like a Gaussian, but every Gaussian looks the same. Every bump looks the same. What actually happens is that the tail of the original signal gets distorted. So this signal what happened is not that this is going there. What happened is that the original tail got distorted to give you this thing that looks like a pulse. And you can test this, for example, if you chop here and don't have this advanced tail and just start your signal here, then you will completely lose this signal. Because causality is a theorem. If your signal vanishes to the right of this, the output will also vanish to the right of this. So that's a theorem. So you can't actually send a signal. And also the other thing that's a theorem is that the magnitude, the norm square of the signal to the right of this line will be preserved. So that's why it cannot be bigger than the original Gaussian. At least the norm square, the RMS amplitude cannot grow. Okay. So the message of this exercise is that causality give you this relation. So I cannot use the blue. Causality relates, well, for scattering amplitude, the real and imaginary part in a very deep way. You really need absorption to be related to whatever real phenomenon you're interested in. Okay? So this relates very part and absorption. Yeah, relate absorption and propagation to any medium that preserves causality. And that's going to be the same when you scatter particles that go through each other. That's the main lesson of this example. But yeah, I think I wanted to give you this approach because you can go through complex analysis to derive this formula, but I think that's kind of intuition why something like this has to be true by causality. Yeah, let's get back to homework 1. So suppose we don't care about action at a distance. So yeah, how do we write quantum theory of gravity? It's actually an interesting exercise. So yeah, I don't know if anyone wants to take a chance. There's no wrong answer. There's no wrong answer. One wants to take a chance. How you write what would you write down?
Would you try and write something to reproduce Poisson's equation? So like -1/2 phi nabla squared phi instead of box phi?
Yes.
And then plus a coupling to rho?
Yeah, that sounds good. Yeah. It's easy. Told you it was easy. Yeah. So you could write something like you could write a theory that's like integral over all whatever your QFT is, and then add some field phi, and then you would have your original action of the QFT, and then you said I should integrate something like phi grad square phi Poisson equation, and then yeah, I could couple this phi to the energy density of the model. Let's say T00. Done. Quantum is gravity. Let me put G. It's gravity. Yeah. Yeah.
You could just take the Hamiltonian constraint from
Yes.
GR and quantize that, and then you got canonical quantum gravity.
Yeah, that will look a bit similar. Yeah, I think does that give you like an instantaneous potential?
Yeah, so
Yeah.
I guess the potential term would just be the Einstein-Hilbert term,
Yes.
right?
Yeah, so I guess it's probably equivalent to effectively adding something to Hamiltonian. So let me manipulate this formula and put it in a slightly different form. So the interaction doesn't really have to come with a field phi. So let's integrate it phi. Let's integrate out phi. That's the same as x above integral s QFT plus some integral over, say, dx dy of T00x, T00y times some potential of x minus y. Okay? And maybe you could put some wave function of t minus t prime, maybe a delta function to put them at the equal time. Right? So this model is equivalent to this model. And what you see from this second formula is that, in fact, this model has a lot of flexibility. In fact, you might not like putting a v equal 1 over r in, because if you put v equal 1 over r, every particle is going to have an infinite self-energy from gravity, and then you'll have to renormalize that, and it's not. You'll have to work to see whether this model really makes sense or not. But we only know that the potential looks like 1 over r up to something like 10 minus 5 meter, where it's actually been measured. So Let's just make a potential that looks like this. That theory will be UV safe. Now I don't have any UV divergence on this potential. That's a UV complete theory. If I started with QFT that made sense, this will also make sense. And just to make sure I don't have divergence, I could put this psi function that be a delta function of time, but really be safe, make it smooth. Works. It's quantum theory, gravity. Let's go on. Start problem solved. It's not a great theory, right? What wrong predictions does it make? What experiments does it disagree with? Yeah.
Disagree with the orbit of Mercury.
Yeah, exactly. The period, the relativistic shift to the orbit of Mercury would go wrong. Yeah. But that's basically a first post-Newtonian correction. So maybe I can fix this by adding some nonlinear term with PPT. I could fix it. No problem. I couldn't tune the coefficient of this nonlinear term in just the right way. I think I can fix that. What is wrong with this theory?
There's no wave solutions?
Yeah, it doesn't have waves, yeah. So maybe I could add like some linearized gravity waves. That allows me bucks. Maybe I could add it by ends and couple them. I think I can add that by ends. Sorry? Yeah.
Is transmitted instantly, like
Yeah,
two-pointer.
that's true. That's pretty bad actually. Yeah, but maybe maybe I could make this potential delayed using the retarded time instead of the normal time. I think I can fix that. So I think you get the point. Is that the basic problem with this framework is that there doesn't have to be any relation between this potential and the waves that you exchange. Because if you don't care about causality, they can be completely independent, and you can just write down whatever you want. You can make any theory that agrees with all data that exists and predict crazy stuff for the next decade of experiments. If you don't care about not violating action at a distance, you can really do what you want. And I think that's really an important challenge for the next years, because we don't necessarily, it's not clear whether causality is an exact property of nature, the Planck scale, what this space-time means. But on the other hand, if we're going to throw it away, if it's not exact, we need some predictive framework. And that I really wish that someone would come up with some creative idea for that. But I think that's one of the big challenges. Sorry for the time. Yeah.
You're saying that causality. So causality tells us there's a relation between the imaginary and real part here, and then the unitarity tells us like the factorization rules.
Going from this formula into this formula is a bit long, but the thing which is a little bit easier is if we go back to the cartoon at the beginning of the lecture, which hopefully I still have. Go back to this cartoon of why we have. No, I don't have it anymore. Go back to this cartoon of why we have. Why we need to have waves, and why the force. Like there was this cartoon where we have the field, the old, and the new field. Remember this cartoon? This cartoon tells you that when you change a force, you can understand the change in the force as a series of two processes. You emit radiation, you absorb radiation. And these little processes, these elementary processes, are actually completely fixed by Lorentz invariance and so on. So this tells you that the force, this is why the force between objects is tied to the way that they can radiate. So it's really this cartoon that tells you there has to be a relation. And yeah, the dispersion relations do something like this, but that's kind of a long technical route. But the reason that there has to be this relation is this cartoon. Thanks.
Okay, let's thank Simon.